Good day, everyone. I am JND Seria, and I'm gonna be your teacher for today's lesson. Okay, our lesson for today is all about the consequences of general relativity postulate. But before we start our lesson, let us first read our learning objectives. For this class, our learning objectives is to explain the consequences of the postulate of general relativity. Example, correct predictions of the shape and orbit of Mercury, gravitational blending of lights, and a black holes. Okay, let's go to our background information. Einstein's general theory of relativity applies the accelerated frames of reference and to gravitation. In fact, the theory comes up with a link between these two types of physical processes that generates to a new interpretation of gravity. I have here two observers. Both of them are standing with a closed elevator. Observer number one is in an elevator that is at rest on the surface of the earth. And the observer number two is an elevator that at rest in a deep space. Figure number one. A frame of reference in a gravitational field, an observer in an elevator at rest on Earth's surface. If the observer drops or throws a ball, falls with a downward acceleration. Or figure number two, an inertial frame of reference with no gravitational field. An observer in an elevator in deep space experiences weightlessness. If the observer releases an object, it remains at rest. If this observer drops an object, it falls toward the floor of the elevator with an acceleration equal to the acceleration due to the gravity. Observer number two stands in an identical elevator located in a deep space. If this elevator is at rest or moving with a constant velocity, the observer experiences weightlessness within the elevator. As shown in a figure number two, if an object is released, it remains in place. Now, suppose the elevator is given an upward acceleration equal to the acceleration due to the gravity as identified in a figure number two, an object that is released now remains at rest. Relative to the background stars while the floor of an elevator accelerates upward towards it with acceleration g. Similarly, if observer number two throw a ball horizontally, it will follow the parabolic path to the floor, just like in observer number one. In addition, the floor of an elevator exerts a force on the feet of observer number one to give that observer an upward acceleration g. We conclude then that the observer number two conduct the experiments in accelerating elevator. The result are the same and obtained by the observer in his elevator at rest on Earth. Einstein extended this observation to general principles, the principle of equivalence. Okay, let's go to the three example for this lesson, which is the consequences of the postulate of general relativity. Our first example is correct prediction of shape and orbit of Mercury. Mercury orbital ellipse is anticipated to change an additional one ring every 2 billion years as a result of formerly unaccounted for effect of general relativity. Mercury orbits of the Sun isn't stable in space. Every 625 years, the ellipse shifts by one ring because its gravitational interaction. Its Newtonian gravitational interactivity with another planet shifts its orbit by 0.15 degrees per century. In addition, as Einstein knowingly predicted, general relativity affects the Sun to Mercury interaction and adds other 0.01 degrees to the planet's orbital precession. Let's go to our second example, which is gravitational blending of lights. Einstein comes up with a theory that a beam of light in a gravitational field must also curve downward. In our solar system, the strongest gravitational field comes from the Sun. Hence, experiments were planned to look for a bending of lights produced by the Sun. To see what influence the gravitational field must have on light, consider the beam of light from the distant star. As shown in a figure, as the light passes stars, it bends as indicated. Gravity's light's bending effect seen in the dance of distant star, because gravity can bend light. The greater the gravitational force, the more the bending. The intermediate galaxy can produce significant bending of light, resulting in a multiple image of the distant galaxy that can form arc or crosses. Okay, let's go to our last example, which is the black holes. The theory of a general relativity foresees that a well-compacted mass can deform space-time to form a black hole. The border of the region from no escape is possible is called the event horizon. Although the event horizon has a greater effect on a plate and circumstances of an object crossing it. According to the general relativity, it has no locally detectable feature. Shows the speed that one could need to surpass in order to escape the black hole's gravitational pull. In other way, a black hole serves as an ideal black body as it reflects no light.